Okay, we're going to be talking about true and false equations, kind of like true and false statements. Exercise 1 says, consider the statement. The President of the United States is a United States citizen. And the statement, is the statement a grammatically correct statement? Okay, and we would say, yes, that is grammatically correct. What is the subject of the sentence? And what is the verb in the sentence? Well, the subject, I'm just going to label, oh, sorry about that. If I can. Well, didn't like that. See if I can move it. No. Sorry. All right, there we go. We can still do this page. We're going to write an S above the subject, which is president. I'm going to try to V above is, because that is the verb. Is the sentence true? Yes, it is. We know that this is grammatically correct because it has a subject and a verb. It is a complete thought. Now consider this statement. The President of France is a United States citizen. Is that a grammatically correct sentence? Yes, it is. Has a capital letter, ends in a period. Okay, it has a subject, which is the president again, and the verb is again is. Now, is the sentence true? No, that is not a true statement. So how are we going to relate this to math? Good question. Okay. If you notice in the very bottom right-hand corner, you'll see that a number sentence is a sentence of equality between two numerical expressions. And a number sentence is said to be true if both numerical expressions are equivalent. That is, both evaluate to the same number. It's said to be false otherwise. True and false true and false are called truth values. Now, consider the statement. 2 plus 3 is equal to 1 plus 4. This is a sentence. What is the verb of the sentence and what is the subject of the sentence? So the verb of this sentence right here, this is the verb. If we read that correctly, we would say 2 plus 3 is 1 plus 4. So what is the subject? The subject would be 2 plus 3. Now, is this a true statement? Yes, because we could also write 5 is 5. That is true. Okay. 2 plus 3 is 9 plus 4. Is this statement a sentence? Well, sure it is. Is it true though? No, it is false, because 5 is not 13. Okay, so we're talking about true statements here. All right, determine whether the following number sentences are true or false. Well, we got to combine like terms. First, is 4 plus 8 equal or is to 10 plus 5? Well, 12 sorry, that is not. So that is false. 1/2 plus 5/8 is 1.2 minus 0.075. Is that true? Well, this would be 0.5 plus 5 divided by 8 is 0.625. And well, honestly, I don't know. So let's just say add those two together, and that's 1.125. Is that equal to 1.2 minus 0.075? 1.125. Yes, that is a true statement. Now, what about C? Now, I don't even have to work this out to tell you that this is a true statement, because I know the properties of mathematics, such as distributive property, commutative property, associative property. And I know that I can regroup this first one like this, or I can completely rewrite it, which is what I actually need to do to show you. And I could actually say 603 times 587 or 5,876 times 71. And I can put that in parentheses, and that still equals 603 times 5,876 times 0.71. Now there's no need multiplying that out, because that's the same thing on this side as it is on this side. So that is a true statement. All right, so here's the question. Can we make that equal here for D? Okay. Well, this is the same thing as saying 13 times 90 plus 85. It's the same thing. Because when we do distributive property, remember, we do it times both of them, which is 13 times 90 plus 13 times 85. Well, so I need to see if this is equal to 175, and it is 175. So yes, this is a true statement. Okay, now remember, on E, this looks like a true statement, but let's make sure. 7 plus 9 squared is the same thing as 7 plus 9 times 7 plus 9, right? So that is the same thing as 16 times 16, which is 256. Now, is 7 squared plus 9 squared 256? Well, that's 49 plus 81. That's not going to get me to 256. So no, that is not one. That is a false statement. That is not true. Actually, that's only, what is that, 130? So that doesn't work out. Now, ooh, pi, is that equal to 3.141? And everybody said no, because pi keeps going and going and going and going and going and going. So that is not a true statement. It's close, but it's not. Pi is never ending. It just keeps going. Let's keep going. Just like us. Okay, now, working with radicals here. This is a very common misconception. A lot of people think we can just break this apart and it will equal each other, and it doesn't. If this was multiplication, it would be fine, but this is not multiplication, because we know the square root of 4 is 2, and the square root of 9 is 3, and so that is equal to 5. But if I said the square root of 13, which is what this is added up to be, right? 4 plus 9 is 13. That is not 5, because the square root of 25 is 5. So this is a false statement. Okay, let's look at K. 3 squared is 9 plus 4 squared is 16. Does that equal 49? So 7 squared is 49. Nowhere close. That is a false statement. All right, let's look at this one. I can already tell you this is going to be false. I better check myself on that. Yeah, I'm going to go ahead and guess and say this is a false statement because when I combine fractions here, I've got to have a common denominator, and that's going to be 6. So that's going to be 3 plus 2, and that is 5 over 6, and there's no way to reduce that to equal that. So that is a false statement. And I'm going to go ahead and look at this one down here because I see that this is the same thing, and that's still not true. That's still going to be false. So it should be 5/6. Not 2 over 6. No, this one's finally true. Look, just done 3 problems just like that. Because I know that this is equal to 5/6. So we're good there. Let's work over here now. 3 squared is 9 times 16. Does that equal 12 squared? Well, 9 times 16 is 144. And I know that 12 squared is 144. So that works. All right. 3 squared is 9 times 4 cubed is actually 64. Does that equal 12 to the 6? Well, 9 times 64 is 576. 12 to the 6 should be way more than 576 because 12 times 12 is 144. And I know times 12 again is going to be way more than 576. So that is a false statement. Not true. False, false. If they're false, I'm just going to put a line through their equation. Okay. Here we go again. 3 times 2 is 9 times 3 times 3 is 9 times 3 is 27. Is that equal? What is 3 to the 5th? 3 times 5. Nope, not 3 times 5. 3 times 3 times 3 times 3 times 3 is 243. Is 9 times 27 243? It is. So that is a true statement. All right. Could a number sentence be both true and false? No way. It has to be either true or it has to be false. All right, so this next one says, could a number sentence be neither true nor false? Could it be neither true nor false? What would be the other alternative? I'm going to go with no way. It has to be either true or false. Okay, an algebraic expression is a statement of equality between two expressions. Algebraic equations can be number sentences when both expressions are numerical, but often they contain symbols whose values have not been determined. All right, exercise 4. This says, which of the following are algebraic equations? Okay, so what does it mean to be an algebraic equation? Let's go back and look. There's that. An algebraic equation can be number sentences when both expressions are numerical, but often they contain symbols. So first of all, we're going to be looking at, is it an do we have an equation? These all have equal signs. Okay. Do they have variables? All of these have some form of a variable, whether known or unknown. Okay. They have numerical expressions. So yes, all of those are algebraic equations. Which of them are also number sentences? Well, what does it mean to be a number sentence? It would mean that we could actually solve them. Okay. Number sentence would mean we could actually solve them, and we could solve all of these. We could solve 2, 3, 4, and 5 because we can plug in a value for pi, right? And we could get an answer. Now, x, we don't know what x is. Okay, so the best we could do is say what? Find out what x is, but that still would just be something like x is equal to, for example, 8.4. And I don't know what that's not a statement. Okay, it's not a number sentence. Okay, I don't know what this is. So 1 is not. For each number sentence, state whether the statement is true or false. Okay, so let's go back up here and see if we can figure these out and see if these are true or false. Okay, now remember, we're not even going to deal with number 1 because we can't deal with that. All right, is this true? Number 2, I don't see how that's going to be true. I'm just going to call that false. I don't know how we could work that out to get the left side to be 99 pi squared, or break down the right side to be 10 pi to the 4th plus 3. Okay, now this one's easy. Number 3, we can do that. Pi plus pi is just 2 pi, right? So 2 pi equals 2 pi. Why is my pen not wanting to work? 2 pi is equal to 2 pi. So that works out. That's a true statement. I'm going to put the line through that one. So first of all, number 2 is false. 3 is true. All right. What about, is 1/2 plus 1/2 equal to 2/4? Well, no, 1/2 plus 1/2 is 1. That is not going to equal a half again. So 4 is false. Look at 5. Oh, okay. Look at 5. I don't think this is going to work out because this side is not going to have a 6 pi. I mean, not going to have a pi cubed. That will not work out. 5 is false as well. All right. Page 8. When algebraic expressions contain a symbol whose value has not been determined, we use analysis to determine whether the equation is true for all possible values of the variables, or the equation is true for a certain set of possible values, or it's never true. Okay, for each of these 3 cases, write an algebraic equation. They be correctly described by that case. Okay, so we could say for A, we could say 2 times x plus 3 is equal to 2x plus 6. That can be determined, and therefore x will be true for anything we plug in. Whatever we plug in for 6 or for x, that's going to equal. Okay, what about x plus 5 equals 11? This is true only for what number? X can only be 6. This x can be any number. X can only be 6 right here. Okay. Now, for C, what about when it's never true? Okay, here's a fun one. X squared is equal to -1. There's nothing that we can plug in for x and it equal -1. Because if we plug in a negative number, that's going to be positive. -3 times -3 is a +9. If we plug in a +3, 3 times 3 is +9. So we can never have a -1 here. Consider the following scenario. Julie is 300 feet away from her friend's front porch and observes someone is sitting on the porch. Given that she did not specify otherwise, we would assume that someone Julie thinks she sees is a human. We cannot guarantee that Julie's observational statement is true. It could be that Julie's friend has something on the porch that merely looks like a human from far away. Julie assumes she is correct and moves closer to see if she can figure out who it is. As she nears the porch, she declares, "Oh, it's our friend, John Barry." Okay. So in looking at that, we have to determine some certain things. So we may not know exactly. We have to work some things out. Okay, that's just a scenario there. So if we look at exercise 6, it says, name a value of the variable that would make each equation a true number sentence. Here are several examples of how we can name the value of the variable. Let W equal -2, then W squared is equal to 4 is true. Okay, that is true. W squared is equal to 4 is true when W is equal to -2. That is correct. So -2 times -2 is 4. The next one is if W is equal to -2. That would also be true. And W squared is equal to 4 is true for W equal to -2 and W is equal to 2. Those are all true statements about that variable. Now, there might be more than one possible option for what number values to write. And feel free to write more than one. Let blank, then 7 plus x is true. Well, that would have to be 5. X would have to be let x equal 5 to make that true. Okay. What does it have to? What does R have to be to make this true? Well, we would have to have 37 divided by 2 would be what? 16 and a half. So R would have to be, let's see here, R would have to be, oh, that's 32.5. 32 divided by 37 divided by 2. Okay, that's not correct. 37 divided by 2 is 18.5. So R would have to be 6. Okay. M cubed, that would have to be, M would have to equal -5. So -5 times -5 is 25, times a -5 is 125, -125. A number x and its square have the same value when it would have to be x is equal to 1 or x is equal to 0. That's the only way that x and x squared would be the same value. The average of 7 and n is -8. So the average, which would mean we'd have to add it up and divide by 2 to be -8. The average of 7 and n is -8. Okay, so n would have to equal -23, right? Because 7 minus 23 divided by 2 is equal to -8. Because 7 minus 23 is -16 over 2. Okay. Now, when will A be true? Here, A will be true for anything. A can be equal to any number. That's going to be a true statement. Okay. Q plus 67 is equal to Q plus 68 is true for. That's not going to ever happen. That's going to be never.